Hello everyone, welcome back to alkaline hydroxide 784, and today we will be covering the three-dimensional vector geometry. Okay, whatever that means. Okay, I know what it means, but lines, okay, fine, lines and planes. The only reason why they put lines in three-dimensional geometry is because they can go through three-dimensional geometry. If you have a cube, you can have a line going right through the cube, and that the cube is three dimensions. So, yeah. Um. Okay. I originally thought of putting this into two parts, but the thing is, lines and planes can be covered together, like instead of separating them. So what I'm gonna do is just do it all in one go. If the video is too long, anyway, you need to watch both of. You need to look at both of them, right? So might as well just watch the whole video. I'll try not to talk for too long because the more I talk, the more I have to spend time recording the drawing, the writing part. And then, yeah, you get the idea. Okay, so let's start with the equations. Those are the first thing you should know about lines and planes, right? I don't think I need to give you a definition of what a line and a plane is, do I? I mean, unless you think planes are the airplanes, which we're not talking about airplanes here. This is maths. A plane is like a flat surface. In of course, in real world scenarios, a plane could be like the plane aligned to your table or to your wall or something like that. But in maths, we look at abstract things, so the plane could be infinite. It could be going in all directions. Sorry, not all directions. It will be just expanding forever. So yeah, just imagine the small region of the plane in which you're actually doing your line cutting or your plane cutting. You don't need to imagine the entire plane. Okay. Okay, so for a line, basically in vectors, a line is actually defined as like a point, and also the collection of points rather than just a line. A line is a collection of points in that in a certain direction, which is defined by a direction vector. So one of the points will be a reference point, which is why the line equation is written with a reference point. Like for example, you can have 1, 2, 3. I do not know why I like 1, 2, 3 so much. So that will be an example for the reference point, and your direction vector could be, for example, 2, 3, 4, and your final line would be something like 1, 2, 3 plus lambda or something else, any scalar unknown that you can use with 2, 3, 4, which is your direction vector. So the reason why we use an unknown like a lambda or we use theta, we probably use lambda, or you can use st. You can use anything that isn't x, y, z. Don't use those. You can use other letters if you want. Yeah, so you can use those kinds of things to rep symbols or letters, Greek letters or English letters, Latin letters. I mean, wait, no, never mind. To represent your your constant, yeah, the constant of proportionality to the direction vector. And basically you understand that this is supposed to be a number, like a scalar, and not some other, not a vector, not some confusing, don't know what else could possibly be kind of thing. So yeah, so it could be something like 1, 2, 3, 2.5, 3.1415, never mind. Yeah, pi. So basically the idea is that each point on that line up to the smallest decimal places of, it could be like pi, for example, each and every single dot, when you combine them all together you get a line. That's why the line equation works. Even though it looks weird, it's like, what is this? Why is there like two different things and the line is just looks like one direct dimension? So that's the reason why it's like that. I hope you understand the idea behind the equation. So it makes it easier for you to remember the equation in a way. So for vectors, sorry, not vectors. Okay, so this is like the the vector equation. So if you want to convert this to a Cartesian equation, you basically need to, you know, bring in the x, y, z of the thing, and for example, you would say x is equal to 1 plus lambda times 2, or 2 lambda in other words. Y is equal to 2 plus 3 lambda, and z would be 3 plus 4 lambda. And from there, you should make lambda the subject in all three of the equations, and you can then equate them together. Like for example, if you have x is x is equal to 1 plus 2 lambda, you can convert it to lambda is equal to x minus 1 over 2. And likewise, you can do it for y and z, and you can equate them all together into an equation. So in this case, it would be like x minus 1 over 2 equals to y minus 2 over 3 equals to z minus 3 over 4. Actually, you don't need to go through this complicated, like elaborate way of doing it. You can do it straight away. You can convert between the two forms if you know how it works. So for example, if you have your vector 1, 2, 3, and you have the direction vector 2, 3, 4, right? So when you have x, y, z, you have to write x minus the thing that's in the position vector and over the thing that's in the direction vector. So for example, instead of 1, 2, 3, you have negative 1, 2, 3. Then you must put x plus 1 because x minus negative 1 is equal to x plus 1. Yeah. So just follow that rule and you will be able to do this without having to think too much. As for the scenario where you have a 0, if the 0 is in the direction vector, you can divide it, right? Technically, you can divide it by the thing. So you just don't include it in the combined equation, and you put it separately. Right? For example, if you have instead of 1, 2, 3, you have 0, 2, 3. That one for that is okay. You can just put x over 2, so you don't need to worry about that. But if in the scenario of instead of 2, 3, 4, you have 0, 3, 4, so you still have 1, 2, 3 plus lambda 0, 3, 4. In that scenario, you would just put x equals to 1, and there's a separate thing from the y minus y minus 2 over 3 and z minus 3 over 4. So there'll be two equations instead of one. So that's how you reason your way of doing the Cartesian equation from the vector equation, like you transition between the two. So I hope this is quite helpful because vectors is generally a topic that people find hard and difficult. Because it's just weird and looks weirdly abstract compared to so many other things that don't seem so abstract, like for example geometry. You can literally see a triangle right there, but in vectors it's quite hard to imagine the plane or the line because they're infinite in a way. They're not, even if you draw the line on your piece of paper, it's not enough. It's not the actual line. It's a 2D representation of the line that is in 3D space. Yeah, how deep. Okay. But if you're interested in this kind of things, you can actually go and look up higher dimensions. There's a lecture on that by the Royal Society. But anyway, that's not important. That's not required for your A level. If you're interested, you can watch it. That's your own decision. Okay, so after we finish the lines, we will look at the plane. So a plane, for lines, we just define how it works. Like we have a point to refer to and a direction vector. So for planes, we need more than just those two because a line is in essence like a two-dimensional thing. You don't have all three a line on its own is one-dimensional. Sorry. Okay, what am I saying? It's one-dimensional. If you put a line on a piece of paper, it will look one-dimensional. But if you put a square, for example, on a piece of paper, it will look two-dimensional. So if you have a two-dimensional object in three-dimensional space, you need two different lines to actually locate the plane. Because if you have only one line, there can be an infinite number of planes, touching that line, like having the line within them. So that's why you need two lines, And in this case, you still have a reference point, which could be where the lines intersect, or it could be another point on the plane. So you have a reference point, and then you have one line, like the first line, which you will create. You already will have a line created by infinite number of points from one direction vector. And then you have the second direction vector, which could be another line on the plane. It doesn't necessarily have to be perpendicular to this line. It just needs to be another line that's on the same plane. So so in that scenario, you will have the second dimension of points going away and in front and behind this one-dimensional line, and that's how you get a plane. I hope I made sense. I don't know. If I guess it's a bit hard to understand what I'm saying, but if you can visualize that, then you will understand why the equation for a plane works as well, and it will make your life so much easier. And of course, we all love the vector, the equation where we can just put, this dot, this equals to this, that equation. We all like the equation, and because from there you can get a very easy way to represent our Cartesian equation. So I'm gonna cover that now. So from this general way of representing the plane with one point and two direction vectors, you now need to get to find the normal. And you remember last time we talked about the cross product, right? We talked about how the cross product works. So in the cross product, you can get a line sticking out from the intersection of two lines, and in this scenario, the line that sticks out is perpendicular to both of those lines. And since we now know that these two lines are part of a plane, that means that line that is sticking out is also perpendicular to the plane and is called a normal. It is a normal to the plane. Yeah, so basically you can find the normal by doing a cross product of the two direction vectors. And from there you can use it to, you can use it to do the simplified version of your equation, which is to have the R. Of course, in all scenarios you'll be using the R to represent the line or the plane. So the R, which is the vector, is equals to so the original one will be like R equals to position vector plus lambda direction vector 1 plus mu direction vector 2 or something like that, where lambda and mu are all real. Please remember to put the all real. But for this one, you will be putting something that's like R dot this normal basically equals to a certain scalar, which would be usually represented by D, I think. D or A or whatever you like. Okay. But you should actually write down the number. It cannot just be an unknown thing unless you really don't know what your vector, the normal is, in a sense. And to find that, you can just pick any point on the plane, like your position point. You can just use that point and you can get the D. You can write down that number and you have your beautiful equation right there. And from there, you can go right to the Cartesian equation, which is basically like, since R is like x, y, z, you can represent it in that way, right? You can have a x, y, and z. You can then multiply x, y, and z with their respective, coordinate in the normal, and you will get, for example, if your normal is 5, 7, 9, then your D is something like, I don't know, 20. Yeah, then your equation would be 5x plus 7y plus 9z is equal to 20. It's so nice. Like, wow. So beautiful. Okay. I don't know why I'm saying that. Okay. So now that you know how to do the equations of the line and the vector, and I spent 14 minutes so far. See, I told you this will take a lot of time. I'm sorry. Let's move to the actual important stuff, which would be, solving questions with this information, I guess. So So a question usually comes in many different parts, and in each part they will ask a certain thing. Like they could ask you all sorts of things, like finding, and according to the syllabus, you'll be asked to find the foot of the perpendicular, or to find the distance between two lines or two planes or something like that, angle, anything. There's many things they can ask. So for each of those things, we have to go through how to do it. Okay. Yeah. So the first one, finding the foot of the perpendicular and distance from a point of a line, from a point to a line or to a plane. Okay, so the foot of the perpendicular, um, basically you have a point. Let's say, yeah, you just have a point. You can use the origin. Let's say we have the origin, and you want to find the perpendicular. You have this perpendicular line from the origin to a particular line or to a particular plane. So if you are going to use a line, it's a lot less complicated. So you just try to you need to know which line is connecting both of them, and you'll get a perpendicular line kind of, because it's the origin. And from there you need to find what's that point on the line that is called the foot. So in this scenario, you would be having, let's say the origin is O and your foot is F. So OF dot the line would be equal to 0, because, wait, is it equal to 0? Yeah, I guess. Okay, so yeah, it should be equal to 0. Yeah, it's equal to 0. It's equal. Sorry, my mind is not working. Okay, because the dot product has a cosine theta, right? So when you have cosine 90, you will get 0. So you use this information to find what OF is, in the sense. And the reason why I'm using the origin, because it makes my life so much easier. So yeah, of course you will, in reality, you will not be using the origin. You may be using some point like 1, 2, 3, some weird fractional point also, who knows. So yeah, this is just for demonstration purposes. Okay, so for OF dot, the line that you have is equal to 0. So from there, since you know what the vector, the line is, it's just that the only unknown you have there is the mil or the lambda or whatever. So just add that into just add those two equations together. So like how we do our x equals to 1 plus 2 lambda, you write the vector as 1 plus 2 lambda. No, actually you don't need to do that. Yeah, let's just keep them separate, sorry. And then for example, your OF will be like, it's not actually F, it's just the direction, right? It's like the line that's perpendicular to this. So you need to find out what that line is, in the sense. Yeah. But OF would also be equivalent to, point F minus point O. And since F, we can generalize it as another equation of the line. Wait, sorry. So for F, right, you would be using this equation, the position vector and the lambda with the direction vector. But when you do the dot, you use the direction vector. Don't include the position vector for the actual line. So you would be writing, since it's the origin, you don't need to, add in or minus anything. If there's another point like AF or BF, then you have to minus OA from OF in order to get the vector AF or BF, or for example. But in this scenario, we are not going to use that, so you'll just be going with OF. So OF would be equal to, for example, 1, 2, 3 plus lambda 2, 3, 4. So where we don't know what the lambda is. And that entire thing is dot product with the only the direction vector, which would be 2, 3, 4. And that is equal to 0. So from there you can do the dot product on the position vector, which is pretty straightforward. In this case, it would be 2 plus 6 plus 12, 20. Yeah, 20. And for the other one, you would be it would be basically squaring it lah. So lambda times the magnitude of the direction, so square of the magnitude of the direction vector. So it will be something like lambda times 1 plus 4 plus 9, 14, yeah, 14 lambda. Yeah, so we have 20 plus 14 lambda is equal to 0, and from there you can find lambda, and then you can get what is OF. And from there you can find out what is F, because, I mean, you've just found out what OF is. If it's like AF or something, then you have to re-minus or re-add the point to find OF. And there you have your foot of the perpendicular. Yay. Okay, and then if you want to know what's the distance, since we found the foot of the perpendicular, the line connecting the point and the line is perpendicular, right? So it's the shortest distance you can get from that point to the line. And using that, you can, if you have a AF or something, you need to find out what, if you have OF, you need to find out what is AF, for example. Like if your original point is A to F, then you need to find out that particular vector in order to find the magnitude and hence the distance. But if you're starting from the origin itself, which is OF, you don't need to do anything else. You just find the magnitude of OF. I hope I made sense. If you have any questions, just ask in the comments. If you find me very confusing, just tell me. I'll try to be less confusing. Yeah. And now we move on to a plane. So how do you do this with a plane? A plane is so much more complicated than a line, right? There's like a whole other dimension. So basically, you find the line, I guess. But the thing is, you can use the normal of the plane. We already have that perpendicular line called the normal. So you use so instead of worrying about the line or anything, you can just say, for example, your AF point would be, let's just use A this time. So we have point A and to point F. So AF is equal to OA plus some multiple of the normal. And you can use lambda or S or T or whatever you like to use. And from there you can say, so from there you will get what the point is on the plane. So since you already know that this is perpendicular to the plane, we can just say this is equal to whatever you write the equation of that plane in the vector equation. And from there you can solve it in your way of solving it, I guess. And you can find out what is your lambda or whatever unknown value that you have. And using that you can find the point. Okay, yeah, cool. So the next one would be to find the angle between two lines, between a line and a plane, or between two planes. For two lines, we use the dot product, which is cosine theta. For a line and a plane, actually we use dot product. So for two lines and for two planes, we use cosine theta. And for line and plane, we will just use the sine theta, because if you use cosine theta, you get the what's the term for it? This is complementary. The angle that, you get the other angle, like 90 minus the actual angle that you want to find. Because you usually want to find the acute angle or something. So if you use sine theta, you will get the actual angle instead of getting the other angle. So just take note of that. If they're two similar things, you can just use cosine. If they're two different things, as in a line and a plane, you use sine. And the reason why you need to do that is because when you're doing it between a line and a plane, the plane you're going to use the normal, right? You won't use the actual plane itself. You use the normal to find it. And the normal is perpendicular to the plane, so it's a different line altogether. So when you find the angle you're using cosine theta, you'll be finding a different angle, and you need to minus that from 90 to get your answer. So if you use sine, you can just get to it directly. But if you find it a bit too confusing, you can just go with the cosine, but just remember to minus the angle from 90. But for two planes, why you don't need to do that is because they are both two normals. So the angle will be like the same angle that you get from the intersection of the two normals. Yeah. So for the lines, they put in brackets coplanar or skew. If the lines are in the same plane, um, yeah, I guess you don't really have to worry too much about it. You can just do dot product like you usually do. But if they are skew lines and they never intersect, then can you get an angle between the two? Well, you have to imagine like as if they are intersecting, but yeah, you have to imagine like they're intersecting, and yeah, I kind of forgot whether you're supposed to actually do it. I think you should still do the calculation. Technically, they don't have an angle per se between them because they're not even intersecting each other. But if they were to be intersecting each other, you can use the direction vectors to find the angle in the sense. Yeah. Um. Yeah. Just follow your teacher on that one. Uh. Okay. So yeah, so finally I'll just give you some tips on how to solve vector questions because I know vector is one of the harder topics and it even stumps me sometimes. So yeah. Basically, vector questions they tend to ask you many parts, and if you know how to do each of the individual things, you can actually get through the question pretty well. And some careless mistakes people tend to make is usually transfer mistakes. Like for example, they write one certain bunch of numbers here, then they write a different bunch of numbers in the next time that they write the same vector. So that will lead to a mistake, or they miss out a minus sign or something else that can lead to problems as well. Oh yeah, there's one question where they may ask you to they'll give you a point on top of a plane and they'll ask you what's the mirror point below the plane or even a mirror line for that matter. So in that scenario, the easiest thing you can do is to find the perpendicular line. Like you have the normal, right? So you find how long that distance is, and for example, if you have lambda that normal and you find out what's lambda, yeah, use the foot of the plane, foot of the perpendicular thing, and you find that lambda, and then you just times that by 2, and whatever line, and if you have the original point, let's say point A, plus 2r, 2 lambda times the normal, you will get the mirror point on the opposite end of the plane. And likewise, you can get a mirror line because the line has the same direction vector. You can just apply the same direction vector on below the plane, I guess. Unless a line is like cutting through the plane, which means you need to find the intersection and you need to find the line that has a equal angle on the other side of the plane but it has a different direction. So yeah. So you need to do those things in order to find the mirror points. And for questions where they may give you information but no diagram, do try your best to draw the diagram because drawing the diagram may help you sometimes, especially if you're a visual learner. But sometimes the question is too easy and you don't even need to draw a diagram, and the diagram might just confuse you more. So you do what you think works best for you and for each question as well. I think that's about it. If you have any questions, I will answer that maybe in a future episode. But I don't think anyone has asked any questions for any of the episodes so far. I don't remember getting any comments. So, yeah, if your question is really small and insignificant, you can just ask me personally, I guess. But I don't think it might be that small and insignificant. It may actually be important. Or you can ask your teachers or your friends if it's possible to actually ask them. But if it's based on my video specifically, then ask me. I can answer the question for you. And if you find any mistakes, also do point them out so that I can correct them either in the comment section or using another video just to say that, oh, I made this mistake or something, just in case. And with that, if you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye.